Hi everyone, my name's David and I'm going to be walking you through part B of the ET1 prac, or the conversion of electrical energy to thermal energy. The aim of this experiment is to use a calorimeter, which is a device we use to measure energy transfer rates, to measure the efficiency of a resistive heating element at heating up some water. And what we've got here is some equipment that we're going to plug in. Just like in part A, you'll be using Pasco's universal interface to record data. And what we've got here is a temperature probe here, which we plug into our sensing device. We've also got a resistive heating element, which is basically just power with a resistor on the end of it. And we're going to monitor how much power and current that we put through this device into the resistor. That will go into our bank. And that way we can tell how much electrical energy we've supplied to the system. And we can use the temperature probe to figure out how the temperature changes over time in the experiment. We'll do that by recording on Pasco, just like we did before, and I'll show you how that works shortly. But I'll just give you a rundown of the equipment and how we need to set this up now that we've done part A. Alright, now we're going to swap the experiment over into the configuration for part B. In order to do that, we have to close and get rid of the part A stuff. So we're going to close the capstone file for part A, and then get rid of the actual equipment that we use for part A, and plug in the equipment for part B. So we're just going to unplug all these inputs. We're going to plug the temperature sensor into input A, and then we'll plug the power input for our system into the signal generator on our source. Once we've got that all plugged in, we'll go and open the part B file up on Capstone, and then that will bring up an interface for us to do the next part of the experiment, which you'll see shortly. So we'll come up and you'll see something with some graphs that look a little bit like this once it's finished opening. And you can see what we're tracking in this case is our temperature, our voltage, and our amperage. Now, having the voltage and the amperage will let us calculate the power. And once we've got the power and we have the time, then we know how much energy that we've put into the system. And we can compare the energy that we put into the system electrically to the energy that we get out of the system thermally and see what our efficiency is. And so I'll show you how to do that next. So before we can conduct the experiment, we need to make sure that we know the mass of the aluminium cup that we're using, as well as the amount of water that we've got. So the lab manual says to put so much water in, about 50 grams. So what we've done here is grab 50 milliliters of water, which will give us 50 grams. And then we can weigh that as well as the aluminium cup that we've got to make sure that we have the right values when we go to do our calculations. So we're going to use the scale here, just measure the mass of our aluminium cup, and we record that on our performer. So it might be difficult to see, but that's 27.7 grams. We'll give you the data for this when it comes around to doing the time, so you don't need to record this number. But we'll also record the mass of the cup plus the water that we're putting in here. So we'll pour the water into the cup, and that should give us 50 grams more than we measured before. It's not precise, it's pretty close, but not close enough. Now, the other thing that's important to note is sometimes there won't be enough water with 50 grams in order to completely fill the cup, and that's normal. But what you do need is enough to cover the thermistor that we've got inside the heating element. Because if it's exposed to air, then it's going to burn out. So we need to make sure that it's completely underwater. And usually we just do that by filling it about 3/4 of the way up the cup. So we've got that here in this case, but you won't always have that. Now, once you've weighed that together and recorded the mass, we're ready to go into the next part of the experiment. You might be wondering why we're not weighing the outer cup, and that's because we're using the outer cup as an insulator, so that you can hold and stir the cup while the experiment is going. So its mass shouldn't actually contribute to the heating in the system, but we'll see how that goes later. Alright, so now we're going to put the rest of the experiment together. So we've got our aluminium cup with our water in it. We'll put it in with a plastic spacer into the bigger outer cup, like so, and then we'll put the lid for our calorimeter up on the top. Now you should see that the temperature probe as well as the thermistor are right here next to each other. We'll put them into the water, and then we're ready to start our experiment. In order to do that, we've got to turn our signal generator on, which we'll do right after we started recording data. So I'll hit record, turn our signal generator on, and then we should see that our graphs start outputting data. So we basically just have to wait here for this experiment to heat up now, because what you can see, you probably not see it very well in the video, but we're already starting to see a temperature increase. Now, one thing you need to do at this point is record the initial temperature. So we started at 23.5 degrees Celsius in this case, and we'll see that the temperature increases over time. And at the end, once it's reached 30 degrees Celsius, we can turn the output off and then see what happens to the curve after the power is stopping applied. So Again, through the magic of editing, we'll skip to the end so that you don't have to wait for this to heat up, and then we'll show you what it looks like when we come back. Alright, so we're getting pretty close to the end of the experiment. We're at 29.6 degrees now. So once it's at 30, we'll stop it and then see what the curve looks like a little bit after that. So we'll get ready to stop it. It's going to hit 30 pretty quickly because it's heating up. Alright, so now we just need to turn our signal generator off so you can see our voltage has gone to 0. As a result, our current is, but we're going to keep recording the temperature data. And so what you should see now is that these two graphs look a little bit different. So one of them has this linearly increasing trend. The graph on the bottom has just a constant value, and that's because we were applying power at a constant rate throughout the experiment. So you can see that this is a graph of power versus time. And if we take the area under that graph, we can calculate the energy that's been consumed in this experiment doing the work to heat up that water. And what you'll see, probably not very well, but it'll show up pretty well in the recording, is that this temperature is actually starting to taper off now that the power is not being applied anymore. And you can see that there is a slight delay in that as well. And that's because as things heat up, they can retain some internal heat within themselves. And so when we apply the electricity, or when we don't apply the electricity, that has a bit of a lag time that's reflected in there. And you can see the same thing at the start of the trend as well. Even though we turned it on here, it's taken a little while to heat up to its maximum internal temperature before it started increasing the heat of the whole water. And so what we can see there is that these would be the two graphs that you would have to plot in a performer. So you would have one graph on the top, which looks like this linearly increasing trend that ends up tapering off. And then the second graph would be this one on the bottom, where you've got the power that's been input over time, and then all of a sudden when we turn it off, it goes to 0. And so we just have 0 power coming out of that for now. All right, so in the next segment, we'll discuss how some of the data analysis for this prac works. All right, so you can see now our experimental run is finished. We've just got to get the data out of it. So the first thing we need to do is find our initial and our final temperatures to find the change in T, or delta T. And we do that by going to the coordinate button here and going add coordinates delta tool. And that'll bring up this thing here, which we can then drag to the start of our data set. So at time equals 0, we have a temperature of 23.4 degrees Celsius. So we would write that down as our initial temperature. And then our final temperature, we can just drag this on to the end of our set and find the maximum temperature, which obviously is 31.1 degrees Celsius, which we've got up here on the right. And then that would give us our delta T of 31.1 minus 23.4 degrees Celsius. So the next part we need to know is how long our power was applied for and how much energy was spent doing that. So what we can do is go down to our second graph here and then find the area under our curve. And we do that by finding the curve area button, which is this one up here. And then we just want to find the area under the curve here. So you can see we've been able to calculate the area under our curve, which is 2,521.85 watt seconds. So this is a watt multiplied by a second. And basically what this means is that we've just calculated a value in joules, because a watt is a joule per second. And if we multiply a joule per second by a second, you just end up with a joule. So we have put in 2.5 kilojoules of energy in order to heat the water up by this amount. So what we need to consider next is how much heat that we've actually generated in the system. We do that by using the equation Q equals mc delta T. We have our delta T values now from the measurements that we took earlier. We know the mass because we recorded it at the start of the experiment, and we know the specific heat capacities, or C, of both water and aluminium. We just need to remember the ratio of the masses, so however much mass the aluminium was and however much mass the water was, and then we combine those together into two terms, which you'll see done earlier in the lab manual. We combine that together to work out how much heat energy that we see in the system, and then in the last part of the analysis we can compare that with the amount of electrical energy we put into the system to see what the efficiency of our heating element in there was. And that's how you do ET1 Part B.